Okay, so, it's afternoon of day 4 of the conference, so thank you all very much for coming. And so hopefully over the next 30 minutes, I will share with you a couple of times that I surprised Richard, which is a pretty big deal because when I was a postdoc, my mentor at Canal Lugalera said, it's really hard to surprise Richard. And so I've done it a couple of times, and so without further ado, let me get cracking. And so, certainly, as we've heard, Richard is a super connector. He's been compared to many people. And so when I was planning my talk, I also thought, well, who on earth can I compare Richard to? So I thought for a bit. I thought of Stanley. I thought maybe not when I read up on him. And I thought, well, Stanley, well, surely I got to compare him to Stanley. So it turned out we had quite a bit in common. So, Stanley is the godfather of modern comics, notably Marvel. Richard is the godfather of modern combinatorics. So Stanley has many influential tomes and numerous prizes, including a Hugo and an Eisner. Stanley has many influential tomes and numerous prizes, including 2 of the 3 Steele prizes, and I believe there's a song that says 2 out of 3 ain't bad. Oh, somebody old enough to get that. Brilliant. Okay, so Stanley made comics a respected genre. Meanwhile, Stanley made combinatorics a respected area. They're both visionary geniuses, and they're friendly and approachable figureheads. And so certainly, we can ask Stanley what he thinks of Stan Lee, but Stanley is not here. He passed away in 2018. So we're just going to have to guess as to what Stan Lee might have thought Stanley could be. Well, maybe Stanley is Stanley's real-life engine one? Oh, for a birthday conference, maybe not. So how about Professor X? Well, as we heard from Catherine's anecdote, he's a genius that speaks many languages and has multiple talents. He's great at evaluating problems and delivering swift responses. So I remember Lou once telling me that they were riding on the subway towards Mittag-Leffler, and between the time when they got on and got off, Richard had actually proved a theorem. As we know from Francois' anecdote, Richard is also telepathic, and looking around, you can see that he has mentored numerous gifted youngsters. And so it's really hard to surprise someone like that, but I did it twice, so we're just going to have a look at a couple of those things. So, given your favorite composition, alpha 1, alpha 2, and so on, we can make ourselves a ribbon diagram. And so the ribbon diagram of alpha is going to be the array of boxes with alpha I boxes in row I from the top. So, sorry, Francois, Christophe, it's a rotation. And what we're going to have is that the leftmost box in row I is above the rightmost box of row I plus 1. So here's the ribbon diagram of 3, 1, 2, 2. And so with this in mind, we say that a semi-standard ribbon tableau of shape alpha is going to be a filling with the numbers 1, 2, 3, and so on. So the rows weakly increase as we read them from left to right, and the columns strictly increase as we read them from top to bottom. And then given a semi-standard ribbon tableau, we can associate a monomial to it. Just going to be x1 to the number of 1s you can see, x2 to the number of 2s you can see, x3 to the number of 3s you can see, and so on. So if we look at our newly found friend here, we're going to get x1 cubed, x2, x4 squared, x5, and x6. And then with this in mind, the ribbon Schur function R alpha is going to be, well, take all your semi-standard ribbon tableau shape alpha, take the monomial corresponding to it, and then add them all up. And so if we wanted to make the ribbon Schur function R21, then the first thing we would do is we'd make all of the semi-standard ribbon tableau of shape 2, 1. So here are all the ones with the numbers 1, 2, and 3. So, I'm from Canada at the University of British Columbia. We're not very rich. I can only afford 3 numbers. And so if we look at this one here, we've got x1 squared, x2. Popping over to the right-hand side, we've got x1, x2, x3, x1, x2, x3, thusly giving me 2 x1, x2, x3, and then I add them all up. And now what we're going to do is we're going to look at an equivalence relation. And so we say that two compositions, alpha and beta, are equivalent to each other if their Irreducible functions are equal. And so then if you delve into one of those influential terms, namely enumerative combinatorics volume 2, then you discover that you have that alpha is equivalent to alpha star, where alpha is just your favorite composition, and then alpha star is just going to be the same thing reversed. So instead of seeing alpha 1, alpha 2, and so on, up to alpha L, you'll get alpha L all the way down to alpha 2, alpha 1. So when else is it the case that alpha can be equivalent to beta? Well, all looks well up to compositions of 8. You indeed find out, as was put out in EC2, that alpha is equivalent to beta if and only if alpha is equal to beta or beta reversed. But at n equals 9, you get this thing right here. So notice that you've got the 1, 2, 1, 3, 2 as the reverse of 2, 3, 1, 2, 1, and 1, 3, 2, 1, 2 as the reverse of 2, 1, 2, 3, 1. But who knows what on earth's going on here? Well, thankfully, we do. Who's we? Well, it's Huey Thomas, Louis Valera, and me. And so what did we find? So, well, for this, you're going to need to know what composing and decomposing compositions were. And so this was really the first time that I had a good chance to talk to Richard. So travel back over 20 years to 2003, where FitStack was in. It was in Sweden. Okay, so, and it was a beautiful sunny day, and there was like this queue. I'm not kidding, there was this bench, there's this queue, like the sort of thing that you'd see at Disney World, but at the top of the queue was Richard sitting at a bench. And so, you know, I'm from out of nowhere, and so I salted along to the back of the queue and I waited, and then at the end, you know, I sat down and I told Richard the story I'm about to tell you. And he was just so kind and generous, and I felt really welcomed into algebraic combinatorics. And, you know, being here this week has certainly confirmed that. So what I told him about was composing and decomposing compositions. So if we want to concatenate two compositions alpha and beta, then what you do is you write down your parts of alpha, then write down your parts of beta. And then if you want to near concatenate alpha and beta, you write down the parts of alpha, then you get your last part of alpha, add it to the first part of beta, and then write down your parts of beta. So for example, 2, 1 concatenated with 2, 1 is just 2, 1, 2, 1, and then 2, 1 near concatenated with 2, 1 is going to be 2, and 1 plus 2 is 3, and then 1. And then with this in mind, we can define the composition of compositions. All you're going to do is you're going to near concatenate alpha 1 copies of beta, then near concatenate alpha 2 copies of beta, and so on, and then just write them all down. So if we want to do 1, 2 composed with 2, 1, then I'm going to have like 1 copy of 2, 1, write that down, then I'm going to near concatenate 2 copies of 2, 1 to get 2, 3, 1. This example right here. And you can certainly have trivial decompositions. Basically, you take a string of 1s, decompose into a string of 1s. Alpha can decompose into 1 composed with alpha, or alpha composed with 1, and m times n can be decomposed into m composed with n, or n composed with n. And so it turns out that, well, we can take any composition, and then the irreducible factorization of it is going to be such that when you look at these factors right here, they only have these trivial decompositions. So, surprise that we were able to give to Richard was that the irreducible factorization of any composition is unique. And moreover, if we now return to our class, then we see that, well, our original composition right here, well, that's 1, 2 composed with 1, 2. Then when we look at the other members of that equivalence class, we see 1, 2 reverse composed with 1, 2. Or we see 1, 2 composed with 1, 2 reverse. Or we see 1, 2 reversed composed with 1, 2 reversed. And so this actually is the classification of Irreducible functions. So we have that alpha is equivalent to beta if and only if, when you look at their irreducible factorizations, then when you go around comparing the factors, you either see the composition itself or it reversed. And so a beautiful corollary of this is therefore the size of every single equivalence class is some power of 2. So with this in mind, then maybe perhaps it's not Professor X. Maybe Stanley is Stanley's real life, well, Hawkeye maybe, because, well, ribbons, couldn't find anything about ribbons, but ribbons can be made into bows used by Hawkeye. And, you know, Richard is a superhero without the need of superpowers, just like Hawkeye. And he's got a really good targeting brain for solving problems, so maybe we could describe Richard as the world's greatest marksman, just like Hawkeye. And he has many tricks to help him succeed, so just like Hawkeye. So maybe Stanley is actually Hawkeye. But maybe not. So now we're on to, well, if it was, we're talking to you, they're happy. Okay, but now we're on to surprise number 2, and this is going to involve these chromatic symmetric functions that we have been hearing about so much. So remember that a proper coloring of the vertices of your favorite graph is simply going to be that, well, the 2 vertices are joined by an edge, they've got to be different colors. And so with this in mind, given a proper coloring, you can associate a monomial to it. So what you're going to do is have X the color on vertex 1, X the color on vertex 2, all the way along to X the color on your last vertex, vertex N. And then with this in mind, then the chromatic symmetric function is simply going to be, you're going to take the sum over all proper colorings, make the monomials corresponding to it, and then add them all up. And so since it's Thursday afternoon, I've made a nice simple example for us to work through. So if cyan is color 1, magenta is color 2, and lime is color 3, then if we look at this coloring right here, we're going to get x1 squared. This one will similarly give us x2 squared, and this one x3 squared. Then these 2 here are going to give me 2x1, x2. These 2 here are going to give me 2x2, x3. And then these 2 here are going to give us 2x1, x3. And so those of you who have delved into Richard's seminal paper on chromatic symmetric functions from 1995 may have noticed the following statement. We don't know a graph which is not contractible K13, even regarding multiple edges of a contraction of a single edge, which is not E positive. Well, we do. So who is we? It is, well, Angel Foley, who is at Laurier University, Samantha Delberg, who was at UBC, now IIT, and me. So, not only were we thrilled, but when we told Richard, he was also thrilled and very surprised, and we got an email back from Richard with a plethora of exclamation marks. So we knew we were onto something. And a couple of years later, it turned out that other people thought that too. So we actually won the Robbins Prize for the result I'm about to tell you. And so this was a particularly big deal because since the award had started, we were actually the first Canadians to win the prize. We were actually the first women to win the prize. And research shows that if you have, and this is all of STEM, some prize that is named after a man, this is your chance of winning it if you are a woman. So this was kind of a big deal. So maybe, therefore, this means that Stanley is actually Stanley's real-life Spider-Man, because, well, the questions about the, I was expecting Gorgie to laugh, but so this K13 is the claw, which is an example of a spider graph. And as we know from the wonderful leadership that Richard has shown over the many years in algebraic combinatorics, with great power comes great responsibility. So definitely something that Richard takes to heart as well. As we know, he has genius level intelligence and is able to make great feats. So with Richard, it's mathematical, unless he's, you know, what Federico saying, rappelling down the canyon, but our actual Spider-Man leaps across buildings, and he has a spidey sense for a good problem. So let's unpack the statement. So here's my claw. And so contracts to the claw is if you shrink edges and then identify the vertices and remove multiple edges, then you get the claw. And so the other part of the problem was, remember, our elementary symmetric functions. And recall our ith elementary symmetric function EI is just going to be, well, you're going to have monomials that consist of I variables where these indices are increasing. And then for any partition lambda, you've got the E lambda of E lambda 1 times E lambda 2, and so on. So if we want to compute E21, then by this definition right here, it's E2 times E1. And then by this definition right here, well, we're going to get a sum of all monomials with 2 variables. And when you're actually looking at the indices, they're going to be increasing. And then E1 is just going to be x1 plus x2 plus x3 and so on. And so we say a graph is E positive if its chromatic symmetric function is a positive linear combination of these elementary symmetric functions. And so, for example, a path with 3 vertices, well, that is E positive, but our old friend the chlor is not E positive because, well, it's got that negative sign right there. And it's actually the smallest graph that's not E positive. So let's return to our question. So Stanley's statement said that, well, we don't know of anything that is not contractible to the chlor and not E positive. So we don't know of anything that lies outside of this Venn diagram. Okay, well, how do we tell that a graph is chlor contractible free? Well, for this, we have to go back to 1987. And so the result of Brower and Feldman says that a graph is chlor contractible free if and only if deleting all sets of 3 non-adjacent vertices, and of course their incident edges, gives you a disconnected graph. So if we look at these 4 right here, then if you actually delete the 3 magenta vertices that are non-adjacent, then notice you'll get disconnection. And if you do the same with the 3 non-adjacent black vertices here, you also get disconnection. And if we look at this graphs and we look at their chromatic symmetric function, then notice that they are not E positive. And so these lie outside Stanley's Venn diagram and are the smallest counterexamples to Stanley's statement. Now, at this point, you might say, well, Steph, that's great. But, you know, this is just a finite number of graphs, and so maybe things get better when the number of vertices go up. So much like Bella said this morning, you really want to be aiming for an infinite family. And so in this case, I'd come back to you and I'd say, well, okay, take a saltire graph. So a saltire graph has a path with n vertices on the left, a path with n vertices on the right, and this configuration in the middle. And then when you actually look at it, it's chlor contractible free. And if you look at the coefficient of ENN in its chromatic symmetric function, you see a negative number. And so again, you're outside Stanley's Venn diagram. But you might say, oh, but hold on, Steph. The number of vertices is n plus n, which is 2n. So maybe that's okay. Well, then I can give you a different family. But then maybe you're going to up the ante. And you're going to say, yeah, but what about a graph being chlor-free? We know that chlor causes trouble. And so remember that a graph is chlor-free if it doesn't contain the chlor as an induced subgraph of the graph. So notice here my saltire graphs are most certainly not chlor-free because here's a chlor right here, but this graph right here is chlor-free because if I try and make a chlor with a vertex of degree 3, then notice that what I end up getting is actually this triangle here, so no chlor, no luck. And then we can actually generalize that to the family of triangular towers. So now what I'm going to have a path with n vertices on the left, a path with n vertices in the middle, and a path with n vertices on the right, triangle at the top, triangle at the bottom. And then when we actually look, then we discover that this graph is chlor contractible free, it's chlor free, and also when you look at the coefficient of ENNN in its chromatic symmetric function, then you get a negative number. And so therefore this again lies outside Stanley's Venn diagram. And so to sum up the second surprise that we gave to Richard, remember the statement said that we didn't know of anything that lay outside of this Venn diagram. But what I was able to just show you is that in actual fact, there are infinite families that lie outside that, both that have an induced chlor and do not. And so even though we've got that the chlor is really central to the Stanley-Stenbridge conjecture in general, E-positivity has nothing to do with the chlor. And so now it is time for surprise number 3. So, having had a look around, discovered people like C. And so, you know, if you can't make it to karaoke tonight, then please feel free to join in right now. Yes. I was, oops. Yeah, we'll just go with the repeated one. I'm a Stanley girl in a Stanley's world. It's a lady calculating conjecture and putting. Okay, we should start it again. You have no idea how often this poor guy has had to practice this song with me. I get to do
This tonight, too.
Yeah. Hi, Ken.
Want to prove the theorem? Let's do it.
I'm a Stanley girl in a Stanley world. It's a lady calculating factorizations and putting multi-numbers like it's electric. When your life's symmetric.
That's so rousing. Let's get counting.
I'm a Stanley girl in a Stanley world. It's a lady calculating factorizations and putting multi-numbers like it's electric. When your life's symmetric. Easy one, here I come, set to pose at the fun. Version 2, order 2, I'll backpedal. With my drive to survive, solve that problem right by. Maybe then I will win a field medal. I can count every day, and I'll see. I'm a Stanley girl in a Stanley's world. It's a lady. Calculating factorizations and putting multi-numbers like it's electric. When your life's symmetric, that's a mountain. Let's get counting. Yeah, that's a mountain. Let's get counting. That's a mountain. Let's get counting. Yeah, that's a mountain. Let's get counting. EC2, ICU, JBT, LRU, network flows, young tableau, red times ending. Where your fans, you're a man, even beat Kel and thanking you, what you do, what the ending. I can count every day, and I'll say, I'm never bored. And you count every day, and you think, you never bored.
That's so rousing. Let's get counting.
Yeah, that's the mountain. Let's get counting. That's the mountain. Let's get counting. Yeah, that's the mountain. Let's get counting. I'm a Stanley girl in a Stanley world. It's a lady calculating factorizations and putting multi-numbers like it's electric. When your life's symmetric, I'm a Stanley girl in a Stanley world. It's a lady calculating factorizations and putting multi-numbers like it's electric. When your life's symmetric, I'm so happy. Let's get counting. Yeah, so mounting. Let's get counting. That's so mounting. Let's get counting. Yeah, that's so mounting. Let's get counting. Oh, I'm having so much fun.
We're just getting started.
Thank you very much and happy birthday.